Imagine you're buying a house. Two houses look almost identical, but one costs rupee 50 lakhs while the other costs rupee 90 lakhs. How does a company like Magic Bricks estimate the correct price? How does Uber estimate your ride fare before the trip even starts? How does a business predict next month's sales? Can a computer learn the relationship between data and make predictions? Yes, and one of the simplest machine learning algorithms that makes this possible is linear regression. Today, we'll understand linear regression from absolute scratch. Machine learning has many algorithms. Each algorithm solves a different type of problem. Linear regression solves one specific problem. It predicts a continuous numerical value. Examples include predicting a house price, salary, temperature, sales, rainfall, electricity consumption, fuel consumption, stock trend, delivery time, or insurance cost. If the answer you are looking for is a number, linear regression is usually the first algorithm we try. Let's look at traditional programming versus machine learning. In traditional programming, a developer writes rules, feeds in data, and gets an output. But in machine learning, you provide the data and the output, and the machine learns the rules. Instead of writing formulas manually, we let the algorithm discover the mathematical relationship on its own. So, what is linear regression? By definition, linear regression is a supervised machine learning algorithm that learns a straight-line relationship between input variables and an output variable. A simple explanation. Imagine drawing the best possible straight line through thousands of points. That line helps us predict future values. Let's look at a real-world example, house price prediction. Imagine we have a dataset mapping house size to price. 1,000 square feet is 40 lakhs, 1,200 is 48 lakhs, 1,500 is 60 lakhs, and so on. What would be the price of a 1,700 square foot house? Linear regression learns the trend from this historical data and then predicts the missing value. Before going deeper, let's understand how a dataset is structured. A dataset is made of rows and columns. In machine learning, we call the inputs features or independent variables. We call the output we want to predict the target or dependent variable. In our example, the feature is the house size, and the target is the house price. If we plot our house price dataset on a graph, we get a scatter plot. Each dot on this graph is one training example. The x-axis is our feature, and the y-axis is our target. The goal of the algorithm is to find the best line that passes through the middle of these dots. Many lines are possible. You could draw a steep line, a flat line, or a line right down the middle. Which one is correct? Machine learning searches for the line with the smallest error. The line that is closest to all the data points at once is called the best fit line. Now for the math, the equation of linear regression is exactly the equation of a straight line from high school math, y equals mx plus c. Let's explain every variable. Y is the predicted output. X is the input feature. M is the slope, which tells us how fast the price increases. And C is the intercept, which tells us the starting point. But what if we have more than one feature? That's multiple linear regression. The formula expands. Y equals b0 plus b1x1 plus b2x2 plus b3x3. Now, house price depends on size, bedrooms, age, location, and parking. Each feature gets its own coefficient, representing how strongly that specific feature affects the final price. How does the algorithm actually find this line? It follows a pipeline. First, it draws a random line. Second, it makes a prediction. Third, it calculates the error. Fourth, it improves the line. Then it repeats this process thousands of times until the line is perfect. This repetitive improvement is powered by gradient descent. To improve, the model must know how wrong it is. We use a cost function, specifically means squared error, or MSE. MSE calculates the difference between the actual values and the predicted values, squares them, and finds the average. The model's entire goal in life is to minimize this MSE value to 0. How does it minimize the error? Using an optimization algorithm called gradient descent. Imagine standing on a foggy mountain and trying to walk down to the lowest valley. You take steps downhill. In math, we use a learning rate to determine how big those steps are, and we use calculus derivatives to find which direction is downhill. After many iterations, we reach the local minimum. Let's zoom out and look at the whole training process. First, we collect data. Next, we split the data. Then we train the model, let it predict, evaluate its accuracy, and finally deploy it to a server. This life cycle applies to almost all machine learning projects. A crucial step is the train-test split. We usually give 80% of our data to the model for training and hide the remaining 20% for testing. Why? To check if the model actually learned the underlying patterns, instead of just memorizing the answers like a student cheating on an exam. Now, let's build this in Python. We will use the standard data science stack. NumPy for numerical math, Pandas for data manipulation, Matplotlib and Seaborn for plotting beautiful graphs, and Scikit-Learn, which provides the pre-built linear regression algorithms. First, we import Pandas and load our dataset using pd read CSV. We pass in our house prices CSV file. By calling df head, we can print the first 5 rows of our dataset to ensure the data loaded correctly and see what features we have available. Next, we split the data. We import train test split from Scikit-Learn. We set x as our input feature, size, and y as our target price. We pass these into the function, setting test size to 0, 2, which means 20% of our data will be saved for testing. The random state ensures our split is reproducible every time we run the code. Creating the model is just 2 lines of code. We import linear regression from Scikit-Learn, linear model, and then we instantiate the model object by calling linear regression with empty parentheses. Our model is now ready, but it doesn't know anything yet. To teach our model, we call the fit method. Model, fit x train, y train. This single line of code triggers the entire gradient descent process we discussed earlier. It calculates the mean squared error, updates the slopes and intercepts, and finds the best fit line. Now the fun part, making predictions. We call model, predict and pass in a new house size, let's say 1,700 square feet. The model crunches the numbers through its learned formula and outputs 68,000,000. It predicts the house will cost 68 lakhs. If we plot our results using Matplotlib, we can see exactly what happened. The scatter plot shows our original data points in blue, and the solid red regression line slices perfectly through the middle of the trend. Our prediction point for 1,700 square feet sits exactly on that red line. How do we know if our model is good? We use evaluation metrics. Mean absolute error (ME), mean squared error (MSE), root mean squared error (RMSE), and the R-squared score. Remember, we cannot use standard classification accuracy for regression because we are predicting exact continuous numbers, so we measure the average distance of errors instead. What are the advantages of linear regression? It is incredibly simple to implement. It is lightning fast to train, even on millions of rows. It is highly interpretable. You can look at the coefficients and understand exactly why it made a decision. It's often the best baseline model, but it has limitations. It assumes a strictly linear relationship. If your data curves in a U-shape, it will fail miserably. It is highly sensitive to outliers. One crazy data point can drag the whole line away. It cannot learn highly complex patterns, which is why we have neural networks. Despite its simplicity, it is used everywhere. Predicting house prices, forecasting salaries based on experience, predicting stock trends, estimating next quarter sales, forecasting weather metrics, estimating medical costs, calculating insurance premiums, and predicting energy consumption for entire cities. In an actual industry project, like a real estate AI, the pipeline is more complex. You start by ingesting a giant CSV. Then you perform data cleaning to handle missing values. You do feature engineering to create new inputs. You train the linear regression model, wrap it in a prediction API using Fast API, and connect it to a React dashboard for users. If you mention linear regression in an interview, be prepared to answer these. What is the difference between linear and logistic regression? What assumptions does linear regression make about data? What is multicollinearity? Why do we use MSE instead of mean absolute error? What is the R-squared score, and how is adjusted R-squared different? When should linear regression not be used? Let's recap. We started with a real-world problem and a dataset. We learned that the goal is to find the best fit line that minimizes the cost function using gradient descent. We split our data, trained the model using Scikit-Learn in just a few lines of Python, made predictions, and evaluated the results using metrics like RMSE. Remember the question we asked at the beginning: can a machine predict the future? The answer is not exactly. A machine cannot see the future. But if the past contains meaningful patterns, linear regression can learn those mathematical patterns and make highly accurate estimates about unseen data. That's why it powers real-world AI systems. In the next lesson, we'll explore logistic regression, where the goal changes from predicting numbers to making intelligent decisions between categories. See you there. Thanks for watching. Subscribe to Learn with VV for more videos.